All right, we found this equation when we said that the rate of change of y with respect to time is proportional to y. We came up with our differential equation, we integrated, and we found this equation, and this equation is an exponential growth or decay model. Do you remember the formula that we worked with last year, the PE to the RT? That is an exponential growth model. It fits the same pattern, PE to RT. But this is the exponential growth or decay model. If K is called your constant of proportionality, C is the initial value, K is your constant of proportionality. And if K is greater than 0, you have growth. If K is less than 0, you have decay. Like radioactive decay. So these would be formulas that you might use for exponential growth, population growth, or if something's decreasing in size, your K, your constant of proportionality, and I did not spell that right, sorry. Your constant of proportionality is less than 0 if it's decreasing in size. Okay, so and say that the rate of change of y with respect to time is proportional to y. So your differential equation is what we started with on our warm-up. This time when t equals 0, y is 2. When t equals 2, y is 4. And we want to find what y is when t equals 3. We're trying to solve for that. Now, we've already integrated this, so we know that our formula is y equals CE to the KT. We did that on our warm-up, okay? Do we know what C is? It's the initial value. What's our initial value?
0.
That's time.
So 2.
2. Initial value is 2. You can plug in. If you don't remember, well, y is 2 when time is 0. E to the 0 is 1, so C is 2. But you don't even have to go through that. If it tells you if time is 0, that's going to be your initial value. So you can go straight to y equals 2e to the kt if they give you a value when time is 0. They won't always do that, but if they do, you can immediately determine what C is. If you're investing money, remember y equals CE to the KT or y equals PE to the RT. Your principal amount is your initial value. What you invest is your initial value. But here we've figured out what C is. I need to know what K is. So we've got to solve for K. Now to do that, I'm going to have to use the second set of information that they gave me. When time is 2, y is 4. So 4 equals 2e to the 2k. Do what?
Something that you don't.
Probably just. Oh, okay. I don't. So here we have 2 equals e to the 2k. And I need to solve it for k. So how do we get that exponent out? Natural log of both sides. So the natural log of 2 is equal to 2k times the natural log of e, but the natural log of e is just 1. so you really don't even have to put that. So k equals the natural log of 2 over 2. Do not use an estimated value for the natural log of 2 over 2. If you're going to have to pick this up and use it several times, you can store that in your calculator so that it gets the exact value. But our equation that we now have is y equals 2e to the natural log of 2 over 2 times t. Now, on your AP exam, you can put a three decimal approximation, but don't use the 3 decimal approximation in calculating something else. Use the exact value when you calculate something else. Whether you store the natural log of 2 over 2 in your calculator as a letter, or you type it in every time. But don't use your approximated value. All right, so now I just want to know when time is 3. So y equals 2e to the natural log of 2 over 2 times 3. And you just have to plug that into your calculator to get an answer. And I see so many calculators out on your desks. Okay, so when you type that all in your calculator, you get 5.657, and for you out there in YouTube land, 3 decimal places. Let's look at a radioactive decay. All right, so we're going to look at radioactive decay, and it's measured in half-lives. Y'all doing that in chemistry?
Yes.
Half-lives. It's the number of years it takes for half of the radioactive material to decay. So it could be thousands of years for half of it to decay.
Once it reaches the half-life, then it decreases really fast. What?
It still has the same half-life. It probably will decrease because you have less to decrease. All right, so suppose we have 10 grams of plutonium.
Ugh, sounds like
And it's an isotope. Yes, it is chemistry. This is 239. And its half-life is 24,360 years.
But the Earth is only 6,000.
Okay. So, we want to know how long is it going to take to decay to 1 gram? Okay, half-life is time, right? So we're going to have to figure out what K is. Our formula that we need to use is y equals CE to the KT, because it's radioactive decay. And let's just think about this. If I have an initial amount, no matter what the initial amount is, let's just say y sub 0 is my initial amount. I want to know how long it's going to take, or I can figure out what K is for half of that initial amount, because we know that time is 24360 K. So if I divide both sides by y sub 0, they cancel. So when you're dealing with half-life and you're trying to determine K, you can just start with this equation. 24,360 is your time. We need to know what K is. So again, you take the natural log of both sides. And K is going to be equal to the natural log of 1/2 over 24,360. That's the exact value. So we want to know how. So now we've got K. We know our initial amount is 10 grams. So y equals 10e to the k. I'm just going to put k because I do have a value for that. T. In fact, if you wanted to in your calculator, you could store that value as k or a or whatever. Remember how to store values in your calculator. Okay, if you type in the natural log of 1/2, be sure you close a parenthesis, and divide it by 24,360. Hit enter, then hit store, and alpha, and whatever letter you want to store it as, which is very handy if you're going to be using that more than once. Okay, we want to know how long is it going to take to decay to 1 gram, so 1 equals 10e, and that was the natural log of 1/2 divided by 24360t. So that's 1/10 if we divide out the 10. Just for time, I'll do kt again. To solve this, what are we going to do? How do I want to solve for time. I'm looking for time. I know what k is. It's right there. How do I get that out of the exponent?
Use the
Natural log of both sides. So the natural log of 1/10 is equal to kt. So time is the natural log of 1/10 divided by whatever we stored k as. How long is it going to take?
80,922.168.
80,920, we'll just go ahead and round that up, 23 years. Long time. That's why things have to be disposed of so carefully. They're radioactive. Okay, and filling out this form, first thing we want to find is k. So take the natural log of both sides.
But where's C?
If we're trying to find k, remember when we did it before, we wanted to know if this is our initial amount, half of that initial amount, the y sub 0 is canceled. So if you're trying to find k, you can use the 1/2 equals e to the kt. I don't know what c is. That's what I'm trying to find. That's the initial amount. So this is going to be equal to 1620k. So k is the natural log of 1/2 divided by 1620. So my formula, y equals c e to the natural log of 1/2 divided by 1620 times time. That's the equation I can use now to find initial amount. Because I have an amount at 1,000 years. 1.5 equals c times e to the natural log of 1/2 over 1620 times 1,000. So in order to solve for c, what can you do? Divide both sides by this,
Let's say 1,000.
1,000. So we would have 1.5 divided by e to 1,000 times the natural log. This is when it's nice to have already stored it. C.
2.301.
2.301 grams. Okay, I'm gonna store that because I need it to find 10,000 years. So if I store that as, I'm going to store it as B, then we've got to find how much at 10,000 years. So we've got y equals 2.301, but I'm going to use the actual amount that I have on my calculator, times e to the k times 10,000. Now, if you'd already stored k in your calculator, it would make this a little bit easier. Just plug that right into your calculator. Second answer times e to the 10,000 times the natural log of 0.5. Divided by 1620. And how much is left?
0.32.
0.32
Or 0.032.
grams. Good. Can you see how sometimes storing things would make it a little bit quicker? Okay, so you'll have some problems like this to do. Okay, so you've got a population of fruit flies that are increasing according to exponential growth. On day 2, you've got 100 fruit flies. On day 4, you have 300 fruit flies. We want to know how many were there originally. How many fruit flies originally? Okay, so we know we're going to have to use y equals ce to the kt. We do know that on day 2 we had 100. So we'd have 100 equals ce to the 2k, just plugging in the information we have. On day 4 we have 300. So now we've got 2 equations and 2 variables. And we can use this information to find what we need. So what I'm going to do is take just some of the algebra here. I'm going to solve that for C. So C is equal to 100 divided by e to the 2k. By that? So now that I have a value for C, I can plug it back in right here. So 300 equals 100 divided by e to the 2k times e to the 4k.
I have a question.
Mm-hmm.
Does it have to, do you have to use that to plug into the 300 one? Can you use the 300 one to plug into the 100?
You probably could.
Like, oh,
I think it would work the same way, but it's probably easier to plug in the lesser number.
yes.
Because this, e to the 4k over e to the 2k, is just e to the 2k. And if I divide both sides by 100, we get 3 equals e to the 2k. And now we can solve this for k. So the natural log of 3 equals 2k, k equals the natural log of 3 over 2. So C is 100 over e to twice the natural log of 3 over 2. So 100 divided by e to the natural log of 3. And e to the natural log of 3 is just what? 3. So we had approximately how many fruit flies?
Like
33. So about 33 fruit flies.
So you don't have to figure out what K is?
We did. This is K.
But you don't have to like.
Okay, your assignment is on page 412. Is that 16 through 20, I think?
It looks like it. It's time for lunch.
16 through 20, 22, and 31 to 43 odd.